Hi class, welcome back to the continuation of our lectures in quantum mechanics. And again, our reference is Introduction to Quantum Mechanics by David J. Griffiths. And I recommend you to get a hold of this book. It will help you in your study about topics in quantum mechanics. So in this chapter, we have studied about quantum mechanics in 3 dimensions. And we have uh, done separation of variables in order to separate the Schrodinger equation into, for example, in spherical coordinate system, we've separated the radial part and the angular part, and the angular part was even more separated with the theta and the phi part, the azimuthal and the polar coordinates of the angle. Then we had solved the differential equations, and we knew that um, associated legendary polynomials are solutions to the polar part, and we also have for the radial part we had associated spherical Bessel functions and spherical Newman function or Neumann function. So those are what we studied, and we also had explored about the hydrogen atom, taking the Coulomb potential between the two particles, electron and the proton. And we knew that there are energy levels of the atom, and that um, when the hydrogen goes a transition from lower energy to higher energy, or from a higher energy to a lower energy to the ground state, for example, it releases some photons that has a certain frequency. So in the continuation of our study, we're going to talk about angular momentum in quantum mechanics. So we start with this one. So in classical mechanics, we have angular momentum defined to be L, which is r cross p, where r is the distance from the center of mass, or center at which um, or the axis of rotation, for example, is the distance from the axis of rotation to the point where we are applying some momentum. So L in classical mechanics, L is just equal to r cross p. This is a special vector product, and the x component of the angular momentum is given by this. We also have its y component. X component is Lx equals ypz minus zpy. Ly is equal to zpx minus xpz. And Lz is equal to x times py minus ypz. But in quantum mechanics, the momentum becomes an operator, and p is just equal to h bar over I, or negative I h bar, partial with respect to some coordinate r. So this is the momentum operator in quantum mechanics. So we can change to the momentum p here into the canonical equivalent of momentum in quantum mechanics, this one. So in quantum mechanics, we have the angular momentum to be defined as this, and its components are Lx, Ly, and Lz. So that is the components of the momentum. So let's look at the eigenvalues of this angular momentum L. So here we have, let's check if Lx and Ly commute. So here we have the commutator between Lx and Ly. Commutator is like, in chapter 3 we studied about an operator AB. This is just equal to AB minus BA. These are represented by matrix, for example, and this one is a commutator, the definition of that. So Lx, Ly, we had to provide a test function because the Lx and Ly are operators. So here you have Lx is defined as this one, and this one is also defined by, this is also the definition of Ly. So let's check. So this is Lx, this is Lx, and this is Ly. So we can operate the partial derivatives on f, and the f would also go here. And then whatever is the result in this case, by the way, it is always safer to multiply because this is the order of multiplication. It should be from right to left. It should be from right to left because sometimes you're doing operations on operator and functions, so we always do the multiplication from right to left. So here you can take the partial derivative of f, and then here also, and then whatever the result here should be operated by this one and this one, same as here, same as this term here. So when you do that, so here it is, you have z. This one here is well, this is now shortcut. This is now shortcut, so you can manipulate this and it will just result to this one. And then finally you will have this result, and then you can cancel this one here because the partial differential, the order of deriving doesn't matter in derivatives. So you can take the derivative with respect to y first, or with respect to x first, then y, or the other way around. It doesn't matter. So they cancel. This one will also cancel here, and this one will also cancel, and also this one will cancel. So you're only left with this and this one. And if you take off the f, you will have this to be equal to this one, and then you have this one is just LZ, the definition of LZ here. Here. So that's the result. So this is the result, LZ. So the commutator of Lx and Ly is just equal to IH bar LZ. You have to cancel the test function. You have to cancel this one. So we have this. So if you also take, by the same argument, you can also take the commutator of Ly and Lz, and that's just IH bar Lx. And for Lz and Lx, that will just be IH bar Ly. So anyway, if you change the order Ly, Lx, this would just be equal to negative negative, or should I just write here, negative IH bar LZ. If you change the order, here you have LX LY, and then here you have LY LX. So from this fundamental commutation relation, the entire theory of angular momentum can be deduced. So therefore, the commutation relation between Lx and Ly is a constant times the Lz. Therefore, there's the three angular momentum, the components of angular momentum, is not compatible with each other, or are not compatible with each other, because they don't have their commutation relation is not zero, for example. So going back to chapter 3, we had the generalized uncertainty principle. When you get the uncertainty of measuring Lx and Ly, or you want to get the precise measurement of Lx or Ly, you will be affecting Lz, because this is if you go back to equation 3.139, that's a generalized uncertainty principle. You will have this. So it's quite awkward to that when you measure Lx precisely, that will affect the Lz as well, and of course Ly. But like for example, if you have time and energy, that is just a constant. Or if you have momentum and space, it's just a constant. But in this case, you affect the third component of the momentum. So it would then therefore be futile to look for the states that are simultaneously eigenfunctions of Lx and Ly, because they don't have, I mean, their commutator is not even themselves, or not a constant. They affect the third component of the momentum. On the other hand, you have the total angular momentum, which is given by this. It's the square of the component, sum of the squares of the components, and that's just equal to L square. And if you get the commutation relation between L square and Lx, this one here, so Lx is just commutes with itself. Ly also commutes, Ly does not commute with Lx. This one is automatically 0 because Lx commutes with itself. This one is equal to this, and this one is equal to this one here. And so you have the commutators of this particular quantities here. So you have the commutators there, and then they cancel because they're just the same. I mean, this one is the same as this one is the same as this one, and this one is just the same as that one, only they are opposite in sign, so they cancel. So L square commutes with Lx, it also therefore commutes with Ly and Lz. So you have this. Or more compactly, you can add all this. So the magnitude of the angular momentum commutes with the angular momentum. So this one is this note is used in this argument here. So therefore L square is compatible with each component of L. So simultaneous eigenstates of L square and Lz, for example, can be found. So you have eigenstates f here, and it has an eigenvalue lambda. You have eigenstate f also here, but it has an eigenvalue mu. So you can find simultaneous eigenstates, the f, with different eigenvalues. So they're compatible. So let's take a look at ladder operator technique on the angular momentum, which is what we used in solving harmonic oscillator in chapter 2. So we define the ladder operator, the raising and the lowering operator. The L plus is defined as Lx plus ILy, and L minus is defined by Lx minus ILy. We take the commutator with we take the commutator of the raising and lowering operator with Lz, this one. Let's take a look. So we have this, and we have this one, which is equal to h plus or minus h bar Lx plus minus ILy. So Lz L plus is equal to h bar L plus, and LZ L minus is negative h bar L plus. That is the commutator. So in this case, you have Z um, Z on L plus. You only just disturb L plus, and for L minus, you only just disturb L minus. And here, of course, L square commutes with Lx and Ly, so it's understood to be 0. So if f is an eigenfunction of L square and Lz, so is Lf plus or minus f, L plus or minus Lf here, because of this one. So let's continue. So far, everything is not that complicated. So let's take a look here. So L square Lf, L square L plus minus F, this is just equal to, because they commute here, you can interchange this one. L square L plus minus is equal to L square L plus minus minus L plus minus L square equal to 0. So you can write this and this that are equal, they are equal. And L square F would just be L square F would just be lambda F. So here, and lambda, and L plus minus F would just be mu. On no, H bar, sorry. So anyway, let's just set aside that. So this is just L plus minus. So this is like L y and Lx acting on F. So here you have L plus F is an eigenfunction of L square, or an eigenstate of L square, with eigenvalue lambda. So here you have Lz Lz acting on L plus F. This is equal to Lz L plus minus minus L plus LZF. These two can be cancelled or can be added. They're just equal to 0. So this one here is H bar plus minus H bar L plus minus F plus L plus minus mu F, as found here. So this one is mu F, and this one is L plus minus F here, this one. So you have now Lz L plus minus F is equal to mu plus minus H bar. So let's just separate that. LZ L plus F is equal to mu plus H bar times L plus F, or LZ L minus F is equal to mu minus H bar L minus F. Here you have L plus is called L plus. This is not an operator plus, this is a subscript plus and subscript minus, subscript plus, subscript plus and subscript minus. Not it's not L plus F, it's L plus F. Sorry, for I have very few space, little space. L plus is called the raising operator because it increases the eigenvalue of LZ by H bar. And L minus is called the lowering operator because it lowers the eigenvalue by H bar. So it will come to a point that when you raise or when you go down, it will come to a point that you will reach the state for which the z component exceeds the total angular momentum, and this should not be. So therefore there must exist a topmost eigenstate and a bottommost eigenstate in which the the momentum will not be, so that the momentum or the eigenvalue of the momentum will not exceed with the magnitude of the angular momentum. So there must be a topmost eigenstate or the top rung, in which L plus, if you operate that on the top rung, that would be 0, and of course at the bottom rung, the L minus acting on the bottom rung would be 0. So here you have LZ acting on the top rung would be HL times FT. L here is called the azimuthal quantum number. Look at here. We can expand this. You have the L here, mu plus L H bar. So that should so this should be your top rung LZ. So here you have this one, and of course L square, if you operate that on the FT, will just give you lambda. So let's take a look at this one. we expand it like this and this one, and then we have L squared L square minus LZ square minus plus I h bar LZ, or L square is just equal to L plus minus L minus plus L square Z minus plus H bar LZ. So this is just, you can write your L square in terms of L plus and L minus and LZ. So if you put the top rung operated by L square, you can use this, the L minus L plus LZ square plus H bar LZ FT. This is just equal to this one. This is 0, and LZ will give you H bar square L square, and LZ will just give you H bar L, and that's times FT. And you can factor out H bar square L times L plus 1 times FT. You just use all these things. You just use all these ideas here, all these things here. This one here, and of course these also. So you can use all these things to calculate the eigenvalue. So you have the eigenvalue here equal to H bar square L times L plus 1. This one. This is lambda. Now, yeah, here it is the lambda. H square L times L plus 1. So if we go back here, we look at this. This is supposed to be the same. This is L H bar and this is L H bar. So you have 1, 2, 3, 4 L levels here. L levels here, and also L levels here, and then you have another level here. The total states that you will have is total number of states is equal to 2L plus 1. So you stretch out from 0 to 1, negative 1, negative 2, and so on, and 1, 2, and so on. So you have 2L plus 1. So that's it. And for the bottom rung, you have the eigenvalue for LZ would be H bar L prime, and for L square FB this would be lambda. So if you again write L square FB, you can use this result here. This one, you can use that, and then you use this here. It will give you a lower rung eigenvalue of that would be H bar L bar L bar or L prime, for example. minus 1 FB. So that's the lambda there. So comparing equation for 113 and for 116, if we compare this one, if you compare this one here and this one, what can you say about L and L prime? L and L prime would just be um, would just be would just have this relationship. This means that going up you have L and going down you have L prime. Actually, when you go down, it will just be negative L. And evidently, the eigenvalues for LZ are mh bar, where m goes from negative L to L plus in n integer steps. So it follows that L is equal to negative L plus n. Hence L is equal to n over 2, and L must be an integer or a half integer. Yeah. So if you have a half integer, you would have even numbers of inner energy states. So 2L plus 1, and if L is 1 half, so 2 times 1 half plus 1, this would be 2 states. So you have 1 half and 1 half here, and negative 1 half, I mean. So your difference here is equal to 1. But if you have L equals um, L equals 2, L equals 2, the number of states would be 2L plus 1. So this is 2 times 2 plus 1. This is equal to 5. So you have 2, 1, 0, 1, negative 1, negative 2. 1, 2, 3, 4, 5 states. How about if your L is equal to 3 halves, for example? So for L equals 3 halves, so you will have 2 times 3 halves plus 1. This is equal to 3. So we have 4 states. So this is 3 halves, 1 half, negative 1 half, and negative 3 halves. So you have 4 states there. So your eigenfunctions are characterized by L and M. So you have here this one, this one here. So this is not anymore lambda. Lambda is equal now to h bar square times L plus 1, and your mu is equal to h bar m. And of course your FLM or FML are just the usual spherical harmonics that we had in the study of hydrogen atom. So L can be 0, 1 half, 0, 1/2, 1, 3/2, and so on. And of course, m will just be equal to negative L plus 1 until L minus 1 to L. So FLM is just YLM, the old spherical harmonics. And this one you can also get the eigenfunction of L plus L minus, and ALM will just be equal to this one. So look at this. If you have a lowering operator FML, it will give you H bar times square root of L times L plus 1 minus M M minus 1 square root times F M minus 1 over FLM minus 1. So it lowers the state, but it only lowers in the quantum number. The L quantum number is not affected. So, and of course, if you do L plus, then M would just raise to M would just be raised by 1. So let's look at the eigenfunctions. We can write Lx, Ly, and Lz in spherical coordinates, and that L would now be in this form, and the gradient in spherical coordinates is this one, which you used in electromagnetism. And of course, R would just be R hat, so that you can, but R hat is R cross R hat is equal to 0, and R hat cross theta hat will just be phi hat. R hat cross phi hat would just be negative theta hat, so that your L would be this one. So we can simplify this to this one. To this one here. And we know that in electromag, if you review, we know that your theta is just equal to this, and your theta hat is just equal to that, and just your phi hat is equal to this. So you can rewrite this one, your L, in terms of the spherical coordinates. The Lx would just be this if you factor out all the I here, and if you factor all the J, here, the J here, you will get this. And then if you factor all the K, you will get this. So your Lx, Ly, and Lz can be written in terms of the spherical variables. So the lowering operator and the the raising operator would now be this one. L plus L minus would be this. But as you can see, there's an identity here. You can write in terms of exponential, sine cosine phi plus or minus I sine phi is just equal to e to the plus minus I phi, so that you can write also L plus minus equal to this, or L plus in this case is equal to h bar e to the I phi partial theta plus I cotangent theta partial phi. So that's it for that. And then for LZ, of course, you have a very simple expression. For LC, we just have this, and so you have this one, and this is just equal to HM, right? In previously we have this, so you have the eigenfunction would look like this. Some functions of theta times e to the I m phi, where m there is again from negative L to L. And so if we put in an eigenfunction, or we say f operated on L in terms of the spherical variables, so you have L plus L minus LZ square minus h bar LZ on F, you will have this expression. You just have to substitute that, and then this is of course equal to h bar times L plus 1, h bar times L plus 1, and of course the function. And then this one is just I to the e to the im phi dg d theta, and this one will just be im e to the im phi g. And we can from here, if you this one is, and this one are is, this derivative is taken from this function. So you can see that it results to the same function. The f here, the f the f here is just equal to this one divided by h bar, or it's just the same function. What I mean to say is that it's the same function. So if we cancel the im phi e to the im phi here, or if we cancel this one and this one, we will have just this. And if we multiply If we multiply by negative sign square, we will have this one. And transforming the equation, this is what we have. And this is just actually the differential equation that would uh, give us the spherical harmonics. So instead of FLM, we will use the spherical harmonics YLM. So that's just showing you that the spherical harmonics are the normalized eigenfunctions of L square and Lz. So uh, so you have this one in the usual Schrodinger equation, and this one is the eigenvalue. So if you have psi or phi, you will get the energy eigenvalue for the Hamiltonian, and for the angular momentum square you will get this one as the eigenvalue, and for Lz you will get Hm as the eigenvalue. It's a long discussion, but what's important is this result. So now let's go to spin. The spin is the angular momentum with respect to the rotation of the particle with its axis. It's not the rotation about the center, it's about the rotation with itself, not about a center somewhere else, but within itself. So that's the spin. In in um, in classical mechanics, the spin is when you, if you know what a top is, when you let the top spin, it just revolves by itself with an axis on its body, revolving on its body. The earth, it rotates on its axis as it revolves around the sun. The earth has a spin, and at the same time it has an angular momentum as it revolves around the sun. The spin, so in classical mechanics, a rigid object admits two kinds of angular momentum: orbital momentum, which is the, like for example the earth revolving around the sun, and the motion on the center of mass, associated with the center of mass, that's the revolution of the planet, and then spin associated with the motion of about the center of mass of the body, and that's called the spin. The angular momentum is denoted by L, or orbital angular momentum, and the spin angular momentum is just equal to I times omega, where I is the inertia of the particle or of the object times its angular rotation or angular speed. So there is actually no description of how spin would look like in quantum mechanics. In classical mechanics, yes, you have spin because particles could be seen by the naked eye, but in quantum mechanics, the particles are too small for the naked eye. There's no such thing as spin, but we can relate classical spin to quantum mechanical spin because they really do have spin characteristics, the quantum mechanical particles. And we call the spin to be the intrinsic angular momentum, and the extrinsic angular momentum is called um, the the is the orbital angular momentum. We know that electrons revolve around, and so for example in hydrogen atom we know that electrons revolve around the proton, but the orbit is of course not spherical or not circular. They have different forms. But for the spin, it's really hard to imagine, but it has spin. It has to have spin. So for the spin, it is um, the the same equation works as with the angular momentum. I mean the orbital angular momentum. The same equation works. So that you have this one, the eigenfunctions are IH bar. You still have the same S Sx and Sy. The commutation relation is that you have the commutator for x Sx and Sy is just IH bar Sz, and you can also find it with similarly for Sy and Sz and Sz and Sx. And like the angular momentum, you have also this eigenvalue equation, and you can see that everything is similar, only that L is changed to S. And yeah, of course M would be um, would be the value of would have the value of negative S to, I mean would have the value of S negative S. So this is just like the angular momentum, and this is your value of S, and M would be that. So just follow this equation, I mean formula, to get the eigenvalues of. You also have a raising and lowering operator for spin here. So every elementary particle has a specific immutable value of S called spin, and for mesons you have spin 0, for electrons you have spin 1/2, for protons you have spin 1/2, for photons you have spin 1, for delta particles you have spin 3/2, for gravitons you have spin 2, and so on. So this is one difference with L and S. One difference. But looking at the formula, it's the same for L and S. They work for the same formula, only that you have to change L with S. But the angular momentum quantum number L for an electron in hydrogen can take any integer value that you want the system to have. If you want to put more energy, then L would change, or if you get some energy from the atom, then L would decrease. And you can change the L by putting in energy or getting some energy, but S for any given particle is fixed. So for electron, the S or the spin would have to be 1/2 all the time. So for spin 1/2, this is the most important case because you have protons, neutrons, and electrons. They compose matter and they have spin 1/2. So you can label a state by this one, spin up, and this one is spin down. You can also use this one, but this is the correct way of putting a spin. So these are the two basis vectors for spin 1/2, and any spin could be written. This can be chi plus and this can be chi minus here. And for general state of spin 1/2 particles, you can express that as sum of this spin and this spin. So you can write it like this. You can write it like this. So you can also write chi plus instead of 1/2 1/2. You can also write this as 1 0, one column matrix, or 1/2 negative 1/2, or 0 1. That's the spin. So if you apply or operate S square on chi plus, you will have 3/4 h bar square chi plus. So this is just S square 1/2 1/2. This is just equal to h bar square times 1/2 times 1/2 plus 1 1/2 1/2. So 1/2 plus 1 is equal to 3/2 times 1/2 is equal to 3/4. So that's just that. And this is also for chi minus. The SZ chi plus would have this eigenvalue, and for chi minus would have that eigenvalue. You can also do this S plus S minus, where your S plus is equal to Sx plus Isy and S minus is Sx minus Isy. So here you can also get Sx and Sy, and you can apply that to chi plus spin up. The spin up, if you apply Sx, it will convert to a spin down, and to a spin down it will convert to a spin up. And for Sy, you will have a complex eigenvalue, which is h bar over 2i, and of course the eigenstate would be spin down. This is spin up. You have here spin down, and then it converts to spin up for the Sy. And if you're using matrix, if you're using this one, you will see that S square is just equivalent to this matrix, and S plus is just equivalent to this matrix, and S minus is just equivalent to that matrix, while your Sx is equivalent to this matrix, this one and that one. And it's actually the familiar Pauli spin matrices here: sigma x, sigma y, and sigma z. So I hope you still remember about Hermitian matrices. Sx, Sy, and Sz and S square are all Hermitian, and of course S plus and S minus are not Hermitian because these are not observable quantities. So chi plus has this equivalent matrix with eigenvalue h plus h bar over 2, and chi minus has this equivalent matrix, column matrix, with eigenvalue negative h bar over 2. So if Fz is measured in a particle in a general state chi, it will give h plus h bar over 2 with probability a square, or negative, this is negative h bar over 2 with probability b square. And of course, they should add up to 1. If you want to get the eigenvalues of Sx, and then you can get the characteristic equation, and you will get eigenvalues of positive negative h bar over 2, which is the same as for Sz. And the eigenspinors would be this one, and that would just be equal to 1 1 1 1 and 1 negative 1 for x. So or this is 1 over square root of 2 1 1, and this is 1 negative 1 times 1 over square root of 2. That's for Sx. And if you want to express a chi in a linear combination of these eigenspinors, you can actually write them this way. You can write them that way. So Sx is measured by its eigenvalue. So the probability of getting h bar over 2 positive is 1/2 a plus b square, and the probability of getting negative h bar over 2 is 1/2 a minus b square. So in this example, suppose you have a spin 1/2 particle in this state, so you can write it in terms of this one. Wait. So for x, for example, you can write it this way. That's the general linear combination for x spinors. So here you have the expectation value for Sx is this one. If you write the the general state in terms of this. Yeah. So here you have SZ is just equal to this. Let's look at SZ, for example. SZ is this one, SZ. Here you can write it like this, like this state, but for Sx, you have to write it like this. Wait, let's clean this. Let's clean everything. For Sx, you have to write it like this. So if you compare that, that's entirely different here. And yeah, this one here, and for the Sx you have this one. Of course the Sy would also be different. So Sx would be this one and this one, and for your Sz would be this one and this one. And so for the expectation value of x, of Sx, then we can write this. We can get the chi plus, or the chi, and the adjoint of the chi, and this one. This is just that one. And this is of course the Sx matrix here. This one here. So these are how you manipulate angular momentum, whether it's the orbital angular momentum or the spin angular momentum or the intrinsic angular momentum, or the extrinsic would be the orbital angular momentum. So when a particle rotates on its axis, body axis, that's spin, and when it revolves around the center, it's angular spin, or the extrinsic angular momentum. I mean, it's orbital angular momentum, not angular spin. So that's it for this lecture. I will just, our next lecture would be electron in a magnetic field, which will be discussed in the next video. So hope you learned something. I hope that you're not confused with what is orbital angular momentum and spin. They use the same formula, but of course they're different. So that's all for this lecture, and see you on the next class.